Welcome to the debate. Today we're diving into a really fundamental question in building performance. How do we actually ensure accurate airflow control in variable air volume systems, VAV systems? And we're focusing specifically on the commissioning, the setup procedures for these, quite sophisticated VAV boxes like the star duct Belimo models that are, well, pretty central to modern building management systems, or BMS.
Mm-hmm. And it matters, right? Because the accuracy of that single VAV box multiplied across a whole building directly impacts energy consumption, temperature control, and whether people are actually comfortable in the space.
Exactly. Which brings us right to the core tension, the central question for today. When we're commissioning these VAV systems, should our primary trust, our main reliance for getting that airflow right, be placed on the factory-certified theoretical constant, the K factor? Or should we be insisting on the mandatory hands-on process of field calibration using physical tools?
My stance is pretty straightforward here. The foundation, the operational baseline, must rely on the scientific precision baked into that theoretical constant and the certified engineering of the product itself. And I see it differently. I'd argue that the factory constant, well, it's just a starting point. Mandatory field calibration, actually verifying with tools like a Flowhood on site, that's absolutely essential for real-world accuracy. Because let's face it, every single installation throws variables into the mix that you can't replicate in a lab environment. The reality on site has to take precedence over the theory. Okay, let's unpack my position a bit, starting with the science. The principle for measuring flow isn't unique to one box, it's universal. Airflow Q equals the K factor multiplied by the square root of the differential pressure, the delta P. Now this K factor, it isn't just plucked out of thin air. It's a precise, unique number published for every VAV size and model, like, K equals 4950 for a size 8 Starduck VAV or 1369 for a size 4. These are calculated using standardized tests, often under specific conditions, like 1.5 inches water gauge, and based on certified data.
And the engineering itself, the physical product, implies a certain level of trust. We're talking about highly corrosion-resistant materials like the ZNAMG body, dampers with EPDM seals, ensuring leakage is minimal, less than 0.5%, even at high pressure. This inherent quality means that theoretical K value should be reliable. So setting up the controller, whether through software or, the Bluetooth app with the correct K factor, the specified min and max flows, like maybe 200 CFM minimum, 1200 CFM maximum. That gives you a solid, repeatable digital baseline needed for the BMS communication, whether it's BACnet MSTP or Modbus RTU. If the box is built right and the K factor is derived correctly, that K factor is the anchor.
I get the appeal of trusting the design, I really do. But my perspective comes straight from the practicalities. And honestly, from the manufacturer's own documentation. Look at the star duct Belimo manuals. They don't just give you the formula. They explicitly state that configuration and calibration are required steps after installation. That's crucial, after installation, to ensure accurate operation with the BMS. There's a reason they mandate that. I come at it from, the field angle. This need for field calibration, it's driven by the unavoidable fact that, and I'm quoting the kind of language you see, every duct system and installation environment is unique. You have to picture the reality of a site. You've got ducts running close to elbows, maybe shorter straight runs than ideal, reducers or kutja, as they're sometimes termed, right before the box. All these things distort the airflow profile and directly impact the actual differential pressure, the delta P, that the sensor picks up. So field calibration, as outlined in sections like 5.3 or 8.3 of typical manuals, it isn't just the nice-to-have check. It's a required process where the TNC team, the testing and commissioning guys, must use a Flowhood or a bolometer. They compare that physical measurement to what the BMS is displaying, and if the difference is more than, say, 5%, which isn't a huge margin, then adjustments have to be made. And sometimes that adjustment isn't just tweaking settings, it might involve adjusting the K factor itself or looking deeper at the delta P components to make the reading match reality. If that factory K factor, combined with the measured pressure, doesn't give you the airflow the Flowhood is actually measuring, well then the theory has to bend to the physical truth of that specific installation.
Okay, you keep emphasizing adjusting the K factor, which to me implies the theoretical constant itself is somehow flawed. I have to push back on that assumption. These VAV boxes, they're built to rigorous industry standards, 880, ASHRAE 130. These standards and the design features like the Starcross Delta P sensor, which is specifically designed for sensitivity and accuracy across the probe inputs, they anticipate minor installation variations and are meant to mitigate their effects. We should be trusting the certified K factor, provided, and this is key, provided the installation follows the manufacturer's basic fundamental guidelines. The documentation is crystal clear on this. You need sufficient straight duct runs, usually something like at least 3 duct diameters upstream, maybe 1.5 diameters downstream, to let the airflow stabilize before it hits the sensor. If the installers don't meet these minimum requirements, then the calibration team isn't fixing a theoretical flaw in the K factor. No, they're putting a Band-Aid on a poor installation. Why should we accept the risk, the liability, of manually changing a certified constant when the real problem is that the installation didn't meet the basic engineering prerequisites for the device to work as designed?
That's a fair point about ideal conditions. But let me ask you this. If the installation guide dedicates a significant section, sometimes multiple pages, explaining why field calibration is necessary, detailing the procedure, and listing it as basically the final critical step before handover, doesn't that imply the manufacturer themselves recognizes that achieving those perfect ideal installation standards is, well, often not the reality on a busy construction site? The field truth, the thing that matters when the system goes live, is that if the flow measured by that calibrated Flowhood is off by more than 5% compared to the BMS display, then the theoretical calculation for that specific box in that specific duct has failed its most important test. That's why the physical measurement, taken right there, right then, becomes the ultimate decider, the arbiter of truth. We're not just fiddling with a number. We are correcting the entire control loop to ensure the owner gets the airflow accuracy they paid for. If we skip that mandatory verification, we risk handing over a system that looks okay on the BMS screen, but is physically delivering the wrong amount of air.
All right, let's pivot slightly then. Let's talk about the core input variable here, the delta P signal itself. Its integrity is absolutely central, regardless of whether you prioritize the K factor or the field measurement.
Yes, exactly. Because the whole formula Q equals K times a square root of delta P, it completely falls apart if that delta P measurement itself is bad. And field experience, unfortunately, shows us plenty of ways it can go wrong. You get the simple things like the little sensing tubes getting clogged with dust over time. Or maybe they get kinked during installation or maintenance. Or, and this is a big one, the high and low pressure tubes get connected backwards. That gives you this infamous negative delta P reading. Delta P, which mathematically makes the flow calculation impossible. It's nonsensical. So my argument here is that relying purely on the initial setup and maybe some digital checks isn't enough. You need that focused, physical scrutiny. The emphasis has to be on the health of that delta P sensor itself. These sensors, like any instrument, can drift. They can develop zero offset errors over time. Small errors maybe, but they add up.
And the only reliable way to catch and correct these subtle issues is through periodic, hands-on checks. The manuals often recommend every 6 to 12 months. And performing functions like the reset zero on the controller, which specifically corrects for that accumulated offset error. Just trusting the initial K factor ignores the inherent physical decay and potential for error in the sensing component itself.
I'm not entirely convinced that view doesn't perhaps overemphasize the manual side and maybe underestimate the sophistication built into these modern controllers. I mean, they use these advanced communication protocols, Belimo MP-Bus, BACnet MSTP, Modbus RTU, for a reason. They're not just dumbly sending a final flow number. The BMS can often be configured to monitor the raw differential pressure value directly, and crucially, it can actively report specific critical fault states. Think about alerts like Loi cambien delta P, a sensor error, or Mustin Hyo, complete signal loss.
This digital oversight provides a layer of protection that minimizes the need for constant manual checks just to catch catastrophic failures. If the sensor starts acting erratically, oscillating wildly, or just dies, the system is designed to flag that immediately. This allows for proactive diagnosis before a major flow inaccuracy develops and persists. So while you're focused on, say, gradual drift needing a 6-month check, the digital system offers a form of continuous, real-time validation of the sensor's basic operational health, confirming the input data for that K-factor calculation is at least plausible.
Okay, digital alerts are definitely good for catching those total failures like a wire break, signal completely gone. I agree there. But they often miss the subtler problems, that slow 5% drift from minor internal wear or a bit of dust slightly restricting a tube. That might not trigger a critical sensor error alarm, but those are exactly the kinds of errors that quietly waste energy or cause comfort complaints day after day because they fall below the threshold for an urgent BMS alert. And this difference in perspective leads us straight to how we define accuracy when it's time for the final project acceptance, the handover. Right. And from my viewpoint, for a truly smart building, accuracy is fundamentally defined by that rich, comprehensive data stream going to the BMS. Once you've input the certified K-factor, set your min-max flow limits, the system gives you continuous data, the calculated flow rate, the actual damper position, the control mode, auto or manual, the live delta P value. That dataset is the foundation. If that core constant, K, is correct derived from standards, and the communication is working, which we can verify digitally, then you have a reliable basis for the smart system, reducing the burden of exhaustive manual point-by-point testing on every single box. I see the logic in relying on that digital stream. I do. But the final step, the one that legally matters for client acceptance, is almost always a contractual requirement spelled out in the commissioning plan. The TNC team must, and here I'm referencing typical handover language, record the calibrated parameters for acceptance. That's the key moment, the liability sign-off.
The client isn't just accepting the K-factor entry, they're signing off based on the documented, actual tested flow values, the ones measured physically with the Flowhood, usually at different damper positions like 0%, 50%, and 100% open. That field-verified flow value, the one written down in the official commissioning report, effectively overrides the initial theoretical input from a contractual standpoint. We're not just, trusting but verifying. We are required to be ready to adjust that K-factor or other parameters if the physical measurement falls outside that critical plus or minus 5% tolerance band. The client accepts the measured physical reality documented on paper, not just the factory theory plugged into the controller.
Well, this discussion certainly throws into sharp relief that inherent tension. It's fascinating, really.
Integrating these highly precise, factory-certified components into what can often be a somewhat chaotic and variable construction environment. My core position hasn't really changed, though. The precise, certified K-factor provides the essential engineering baseline, and the digital integration, through protocols like BACnet, offers sophisticated monitoring and, importantly, automated diagnosis of major sensor faults. This allows us to maintain accuracy, ideally, without constant invasive physical checks, provided we trust and adhere to the design standards and installation requirements.
And from my side, the discussion just reinforces the critical, and I'd argue non-negotiable, need for that rigorous field work.
Because the complexities of real-world duct installation frequently deviate from the ideal lab conditions, and because we know these delta P sensors have documented vulnerabilities, drift, clogging, even catastrophic reversal leading to negative pressure readings, physical verification by the TNC team using properly calibrated flow measurement tools remains the only definitive way to guarantee that required plus or minus 5% accuracy. That's the accuracy the BMS ultimately relies on for the building to operate efficiently and comfortably.
Ultimately, I think we both agree that the fundamental calculation Q equals K times root delta P is absolutely central to how these VAV systems function.
Indeed. The real disagreement, it seems, boils down to authority. Does the primary authority lie with the foundational input derived in the factory, the K-factor?
Or does it lie with the necessary final verification of the physical output, the measured airflow on site, in defining what accurate means for that live operating system?
It's clear we need to keep examining these trade-offs. Balancing the benefits of rigorous factory standardization against the unavoidable realities and challenges of site-specific commissioning is crucial if we want to consistently deliver high-performance HVAC systems